So next we're getting into Chapter 7, which deals with entropy. Entropy is kind of an abstract topic. It's hard to understand. I would think of it as just a measure of disorder. A measure of disorder. Or it could be thought of as a measure of multiplicity. That's just, we won't get into that, but that just means there's more combinations, many different ways to produce the same situation, the same scenario. Or also, it's the measure of the thermal energy that is unavailable to be converted to work. That is. All right, and we know that the second law of thermodynamics states that the entropy of the universe is always increasing. But even if we're not talking about the universe, the entropy of an isolated system is basically everything is everything is encapsulated into that system. So also the entropy of an isolated system, a system that is isolated, that cannot feel any of its surroundings, any of its boundaries, is also always increasing. All right, so this gives processes a direction because it must occur in the direction of increasing entropy. Must occur in the direction of increasing entropy. All right, so we know that processes, have a certain path, a certain direction, a certain direction that it wants to go, and that's in the direction of increasing entropy. All right, so even way back to 1865, Clausius came up with this inequality. He figured out, he noticed that the integral over a cycle of this value of this delta Q over T, that's just a lowercase delta, infinitesimally small differential change in Q, heat transfer. If he integrated that over the whole cycle, he found that it was always negative or zero. It was never positive. All right, so let's write this integral in words. Now this thing right here is just an integral, so this is integration over the whole cycle. Right, if something's going from 1 and then eventually it comes back to state 1, if you integrate it over the whole process, it's a cyclic integral. So let's write this equation in words. It's the cyclic integration, or the cyclic integral of delta Q divided by temperature is always less than or equal to 0. The sum of all the differential amounts of heat transfer, Q, divided by the temperature is always less than or equal to 0. Okay, so this cyclic integration of delta Q over T, so it is actually equal to 0 when we have a reversible process or just an internally reversible process. So if something is totally reversible or internally reversible, then it turns out that this integral, this cyclic integration delta Q over T, is equal to 0. If something is irreversible, which is what most of our processes are, then we're going to find that that integral is negative. But the cyclic integral, delta Q over T, this never happens. This is impossible. It's never positive. So what Clausius realized was that this quantity of delta Q over T of a reversible process, it came back to 0 no matter what path it went on, whether it went from 1 to 2 to 3 to 4 to 5 to 6 and back to 1, or just from 1 to 2 and back to 1. As long as it came back to 1, it was equal to 0, and so it didn't change. It was independent of the path of a reversible process, right? It was only dependent on the state. And so he realized that this is a new state variable. So let's say he discovered a new state variable, a variable that is independent of the path. And we're going to call this entropy. We're going to call this entropy now. And we're going to call entropy S. So let's say entropy, a measure of disorder, is defined as S. And so we're actually going to define this as ds, a differential and infinitesimally small change in S, is equal to delta Q over T of an internally reversible or totally reversible process. Alright, so ds is equal to dq over T of an internally reversible process. So if we took the integral of both sides, then we would have S2 minus S1. All right. So the change in entropy, S2 minus S1, and we need to take the integral of that delta Q over T, is equal to the integral of delta Q over T from 1 to 2 of an internally reversible process. So let's box this in, and let's write this in words. The change in entropy. The change in entropy is defined as the integral of delta Q over T along an internally reversible path. Okay, now these could be capital S total entropy or lowercase s specific entropy. So capital S, we'll just call entropy, would be in kilojoules per K. You notice that this is per temperature. And lowercase s specific entropy has units of kilojoules per kilogram K. So it's a little bit different than some of our other properties. Because of this, it's per temperature, per Kelvin. Okay, but that's pretty tough, right? You know, this is the change is equal to an integral of delta Q over T. But we're lucky that there are some special cases. All right, so for an internally reversible isothermal, right, so temperature is constant, heat transfer, delta Q is just Q over T. All right, so we can find the change in entropy of a process of an isothermal heat transfer process is just equal to Q over T. Q in is positive Q, Q out is negative Q. All right, so let's do an example real quick. So we've got a piston cylinder device that contains a liquid vapor mixture of water at 300 Kelvin. During a constant pressure process, 750 kilojoules of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. To determine the entropy change of water during this process. So we have a piston cylinder device. It contains a liquid vapor mixture, so it's kind of under this dome. During a constant pressure process, so if we have a constant pressure process of a mixture, then we're going somewhere from here to here on our TS diagram, or if this is a constant pressure process. So if this is a constant pressure mixture, if it stays a mixture, then it is constant temperature. It is constant temperature. So for this constant temperature heat transfer process, our delta S is just Q over T. Our delta S is just 750 kilojoules is our Q. Positive Q because it's Q into our system, divided by 300 K. 2.5 kilojoules per K is the change in entropy of the water during this process.